Now we have another example looking at different types of continuity and discontinuity. And here we are going to consider the function f of x, and it's a piecewise function, where f of x equals x squared plus 3x if x is greater than or equal to 1, and f of x equals 2x if x is less than 1. All right, so that is our function. And we could look at this with a graph, but we're going to try doing this algebraically, see if we can do it just knowing the properties and definitions of different types of continuity and discontinuity, rather than always having to go draw a graph. Okay, so remember our definitions for continuity overall being continuous at a point, being continuous from the right, being continuous from the left. All of this depends on the function value and limits. So you can guess maybe what the point is that we need to focus on here. The place where we're liable to have a discontinuity would be at x equals 1, because that's where we're going to be shifting from one piece of this function to the next. Okay? Individually, the different pieces of the piecewise function are continuous in their own right. X squared plus 3x is just some parabola. 2x is just a line. There's no real issues with those. It's in jumping from the parabola to the line, or the line to the parabola, that we might have a problem. Or we might not. We'll find out. Okay, so let's calculate some things here. For starters, let's get the function value at that point that we are interested in, f of 1. Okay, so when x actually equals 1, we want to use this piece of the function, so we need to use that upper portion and calculate the value. 1 squared plus 3 times 1. Okay, so that equals 4. F of 1 is 4. Now, we would like to calculate the limit of our function. And we are focusing on that same point, x equals 1 still. So it's the limit as x approaches 1 of f of x. And in looking at that, remember our tricks. Okay, first trick for limits, try direct substitution. Well, we did already substitute, but that was just to find the value of the function. This is piecewise, so we can't really direct substitute per se. Yeah, can't really factor and cancel. There's no conjugate. Probably don't want to sandwich that. That seems odd. So let's look at the one-sided limits on this. The limit as x approaches 1 from the right of f of x, approaching 1 from the right, that would be, okay, here's 1, here's the right. So that would be values that are greater than 1. So that would mean we need to use this upper portion of the function again. Okay, so that would be the limit as x approaches 1 from the right of x squared plus 3x. Okay, and then we can direct substitute and we would come up with 4. And then the limit as x approaches 1 from the left of f of x, okay, 1 is right there. From the left, that would be values that are less than 1. So we are going to need to use the other piece of the piecewise function. Bet you could have guessed that. All right, limit as x approaches 1 from the left And now we just get to use the piece 2x. And you can direct substitute into that and just get 2, because 2 times 1. Okay, so after seeing those one-sided limits, what can we conclude about the overall limit right here? If you said does not exist, you are correct, because the one-sided limits don't match up. So our overall limit, whoops, right there, does not exist. Okay, so in looking at our first part of this question, is f of x continuous overall at x equals 1? No, it's not going to be, because our limit doesn't exist. And that was a key part of the definition of being continuous overall at that point. Okay, we needed to have the limit exist. So let's go down and put that conclusion. Is f of x continuous overall? No. And that is because the limit as x approaches 1 of f of x does not exist. Okay, so now let's break that down a little more and see if x is continuous from the right, from the left, or neither at x equals 1. Okay, so our continuity from the left and right, recall, followed almost the same definitions, but instead of it being a general limit, it was either a right-hand limit or left-hand limit equaling the function value. So that is going to determine our outcome here. Okay, our function value equals the right-hand limit. Both of those are 4. So we have continuity from the right. So continuous from the right. Continuous from the right and not from the left. Okay, because the function value only equals that right-hand limit value. So we can say because the limit as x approaches 1 from the right of f of x equals f of 1. Both of those equal 4, so that's good. Okay. Now, next part. If f is not continuous at x equals 1, classify the type of discontinuity. So for starters, f is not continuous at x equals 1. We've established this. So we do have to classify the type of discontinuity. We don't get out of that. So let's go back to our discontinuity classification chart. Okay, we definitely have a discontinuity. Our overall limit did not exist, so we do qualify for this. Now, we have to decide removable or non-removable. And if it was removable, we would have been able to quickly fix the discontinuity. We could like factor and cancel out something. It's just making a hole in the graph. Ultimately, the limit is there. It's just that the function value doesn't fill in the hole in the graph. So in our problem, we don't have this type of situation. It's a little more ingrained than that. All right, our limit doesn't even exist. So let's see, we definitely have one of these non-removable types. Now, if it were an infinite discontinuity, a vertical asymptote type of situation, Vertical asymptotes, we tend to find where the denominator of something equals 0. On a vertical asymptote, it's not possible for the function value to exist. So we couldn't have f of c. In our problem, we actually had a value for f of 1. F of 1 was 4, so it's not an infinite discontinuity. Okay. We can probably also remove the possibility of an oscillating discontinuity. We don't have a trig function. The function we were looking at is piecewise. It's a line and a parabola, basically. So not oscillating. And therefore, that leaves us with a jump discontinuity. You can definitely see that from the one-sided limits as well, how the limits jump from one value to another. So a limit of 2 versus a limit of 4. That's the difference or the gap between those jumping pieces. Okay, so we have a jump discontinuity at x equals 1. Okay, jump discontinuity. Okay, now describe the set of x values where the function is continuous using interval notation. So this is like the piecewise example that we did right here, okay? So the intervals of continuity are all the little bits in between the discontinuities. And in our case, our function only has one discontinuity. So as we're looking along our x values, the function is continuous, continuous, continuous. This is the part of the function that equals 2x right here. It was not continuous from that side, but then from the right, the function was continuous. All right, we had this match up here. And then it's a continuous function going on from there. So we have two intervals of continuity. One goes from negative infinity to 1, not including 1. And then the other one is from 1 to infinity. We do get to include 1 in that interval since we have that continuity from the right.